For our listeners out there, today's mission is to dive deep into a new architecture called QNodeOS.
Yeah, think of it as trying to be that base layer that'll let tons of different quantum network applications run.
And not just on one kind of quantum hardware, but on various platforms, all using software that's at a high level.
And I think that's a huge step toward taking quantum networks from the lab, where they're mostly at right now.
And making them actually useful in the real world, practical.
Exactly. Practical.
Then, to understand how big of a deal QNodeOS could be, it helps to think about something we all use, the internet.
The internet. Good old internet.
Remember how revolutionary it was when we started being able to program all sorts of applications?
Oh, yeah.
Using high-level languages?
Totally.
That's what really unleashed the power of the internet, right?
Right.
Because we could ignore all those messy hardware details. It even gave birth to whole new areas of computer science.
I mean, think about it.
And that's what QNodeOS is aiming to do for quantum networks, to be that foundational layer.
Yeah, to let a lot more people start building and experimenting with these applications.
Without needing to be quantum physics experts.
Right.
But building a system like that for quantum networks, well, it's not a walk in the park, right?
Not at all. There are some really tricky challenges unique to the quantum world that any system like this needs to overcome.
And honestly, understanding those hurdles makes this approach even more impressive.
For sure.
So let's unpack a few of these challenges. One that jumped out at me was this idea of interactive classical quantum execution.
Yeah.
In the context of quantum networks, what does that actually involve?
What's fascinating here is how much back and forth communication there needs to be.
Between what?
Between the classical computers and the quantum processors.
Right.
In many of these quantum network applications people are imagining. Think about that example you mentioned, secure quantum computing in the cloud.
Yeah.
You have a server with a quantum chip. It's not just working by itself. It needs to wait for instructions from a client program.
Okay.
Or data from the client before it can even start the quantum computation. And this is pretty different from a lot of the quantum computing we see today.
In what way?
Where a program is often run as a single job without needing any input from outside while it's running.
Okay.
In normal quantum computing, while you have those classical and quantum interactions, they're usually very predictable. And at a much lower level, like an error correction or when you make measurements during a quantum circuit. But in network applications, you have these high-level interactions.
So the qubits are kind of hanging out, waiting for instructions.
Yeah, and they need to maintain their delicate quantum state, their coherence, while they're waiting for information from across the network. It's not just about sending quantum bits around. It's about the classical control happening in real time to make everything work.
It's the coordination.
It's the coordination, yeah.
Okay, so that's one challenge. Another one is the whole different hardware platforms issue.
Oh, yeah, that's a big one.
Quantum tech is still so new, and there are just so many different ways to build these systems.
Lots of different physical systems.
Exactly.
Yeah.
How can QNodeOS handle that kind of diversity?
That's where the idea of a hardware extraction layer comes in.
Okay, break that down for me.
Well, think of it like a translator. This layer, it's called the Q driver. It's the only part of QNodeOS that actually needs to understand the specifics of a particular quantum hardware platform.
So it takes the high-level instructions.
Yes, which are hardware independent.
And translates them.
Translates them into the very specific physical signals that a particular Q device understands. And Q device is just what we call the quantum hardware itself.
Okay, that makes sense.
So the Q driver is key to making quantum networks accessible to a lot more developers.
Even if they don't know a lot about quantum hardware.
Yeah, exactly. That's a huge step toward making practical applications possible.
It's like a universal adapter, right?
Exactly,
Yeah.
letting different devices work together.
I like that. Now, another tricky thing seems to be the vastly different timescales involved.
Timescales, oh yeah.
We're talking about network operations taking milliseconds.
Right.
Quantum operations happening in microseconds. And then low-level control going down to nanoseconds.
Nanoseconds, it's crazy.
How can one system even manage all of that?
This is where the architecture of QNodeOS really comes into play. It's logically divided into three main parts.
Okay.
The CNPU, that's the classical network processing unit.
Got it.
The QMPU, the quantum network processing unit.
Okay.
And of course, the Q device.
Actual hardware.
Yep. So by separating things this way, each part can be designed to work at its own pace.
Like different gears turning at different speeds.
Yeah,